Hi, hi, everybody. We're rolling now into chapter 3, and we're at 3.1. And before I start 3.1, I just want to remind everyone that we had a situation. This is back in the second chapter. We learned that if A is a 2 by 2 matrix, A, B, C, D. So we learned that the inverse of A, and we figured this out, is 1 over AD minus BC times this new matrix, D, negative B, negative C, A. And we did that back in, like, I don't know, I think section 2.3 or something like that. And, well, turns out that this quantity here, this right there, you see where it says AD minus BC, that actually is a very important number or figure, or whatever you want to call it. That's actually called the determinant of the matrix. And there you go. And that's what section 3.1 is all about. In fact, that's what chapter 3 is all about, determinants. And it turns out that the determinant is quite a useful concept. And we're going to be able to do some really amazing things with determinants. So with no further ado, let's get into chapter 3.1. Anyway, here's the official definition of a determinant. So if you have a 2 by 2 matrix, so you have A11, A12, A21, A22. So it's A11, A22 minus A21, A12. That is the 1122 minus 2112. And kind of like I always think of it, and they kind of you zip down this diagonal to get the first number, and you zip up that diagonal to get the second number. That's how I always think of it. And let's look at some examples of figuring out the determinant. Now, why determinants are important, believe me, we're going to get into that quite a lot. But right now, I just want to show you how to figure out a determinant. So here we have a matrix 2, negative 3, 1, 2. We want to find by the way, determinant. Sometimes we it looks like an absolute value sign, kind of like just straight vertical lines. So if you write the A with the determinant sign around it, that means determinant. Or another thing you do is that you write the matrix, but instead of writing brackets that have little tabs on top and bottom, you just write straight lines. So when you have just the straight lines there, that means determinant. Now, one thing that's very important to realize is that this here and this there look very similar, but they're not, because this is a matrix. This is a number. A determinant is not a matrix. A determinant is just a number. And it's a number that's achieved from a matrix or generated by a matrix. I don't know how to say it better than that. And so we'll go 2 times 2, that's right there, then minus 1 times negative 3, which if we work it out, that becomes 7. And here we have, now this one is going to be 0, because 2 times 2 minus 4 times 1, which is 0. And this last sucker down here, let's see, that's going to be, well, 0 times 4 is just 0, and 2 times 3 halves is 3, but it's 0 minus 3, which is negative 3. And there you go. So sometimes you see, sometimes a determinant can be positive, sometimes a determinant can be 0, sometimes a determinant can be negative. They're all possible. Even though I said that these kind of look like absolute value signs, they're not actually absolute value signs, they're determinant signs, at least in this context. Okay, moving on. Here we go. Now, minors and cofactors. See, determinants, I should have mentioned, maybe a determinant is only relevant to a square matrix. Whenever we talk about determinants, we're only talking about square matrices. There's no such thing as a determinant of a non-square matrix. So if you have a rectangular matrix which is not square, there's no such thing as a determinant of that. Anyway, now a square matrix, so it doesn't have to be 2 by 2. I just showed you the determinant for a 2 by 2, but you can have a 3 by 3, a 4 by 4, a 5 by 5. You can have any kind of matrix. And how do you find those determinants? Well, a convenient way to do this is using something called minors and cofactors. Minors and cofactors. So if A is a square matrix, then the minor, Mij, of the entry Aij of the matrix, right, is the determinant of the matrix obtained by deleting the ith row and the jth column of A. So let me just show you what I'm talking about here. Here's the minor of A2. I'll do the cofactor. I'll read the cofactor in a second, but let's do minor first. The here's A21. And I draw a line here and I draw a line there to get rid of all those numbers. So I'm deleting the second row and the first column. And I'm left with A12, A13, A32, A22 right there. And the determinant of this 2x2 matrix is called a minor. And if I want to find M22, so I look at A22, again, I just delete anything that's in the same row in the same column. And these numbers, A11, A13, A31, A33, those are the numbers right there that go into that matrix, and I figure out the matrix. Then you do the matrix, the 2x2 matrix, you do it the regular way you've always done it before. Now, cofactor is really kind of the same thing as a minor, only it has a plus or minus one attached to it. So cofactor ij, Cij, that's of the entry Aij, is Cij is equal to -1 to the I plus j power times Mij. So basically, the cofactor and the minor are kind of the same thing. It's just that a -1 to the I plus j power sometimes will be +1, sometimes will be -1, depending on what I and j are. So here we go. Let's look at some examples. So here's A. A is this matrix right here. 0, 2, 1, 3, 1, 3, -1, 2, 4, 0, 1. Oh, before we go on, there's a pattern here. You see this here, this right here, that's A11. Well, 1 plus 1 is 2, and -1 to the second power is +1. This here is A12. Well, 1 plus 2 is 3, and -1 to the third power is negative. So you're going to have this, you're going to kind of have like an alternating pattern, and it's going to go in both directions. And if you have a 4x4 matrix, you're going to have a similar alternating type of pattern. This is a good thing to just remember. And if you have a 5x5 matrix or an n by n matrix, you're going to have a similar kind of pattern of plus minus, plus minus, plus minus, plus minus, in terms of the because this is let's say this one right here. This is 5. This is the fifth row. Yeah, fifth row. This right here is the fifth row, third column. 5 plus 3 is 8. -1 to the 8th power is positive, and so on and so forth. That's how this works. But you want to getting a sort of an alternating plus or minus situation. Anyways, the minor M11. So you go to A11, which is in this case is a 0. You knock out the row in the column that A11 appears in, first row, and the first column. You're left with -1, 2, 0, 1, -1, 2, 0, 1, and this is just -1 minus 0, which is -1. So M11 is -1. Now C11 is also going to be -1 because it just stays the way it is. And you could I'll leave this as an exercise for you. These are what all the minors turn out to be. And the cofactors will basically, -1 will stay the same, the 5 will stay the same, because we're kind of following that pattern. We had the plus minus, plus minus. So -1 will stay the same. This will become, as a cofactor, will become +5. Actually, let me bring the screen up a little bit. So the -5 becomes +5 because it's in that position. The 4 stays the same. The -8 becomes +8. The -6 stays the same, and so on and so forth. The ones where there's a plus stay the same. The one where there's a minus is going to switch sign. That is the way it works. Okay, moving on. Now, the determinant of a square matrix is right here. Here's the definition for the determinant of a square. The determinant of A is an n by n matrix, is going to be the sum as j goes from 1 to n of A1j, C1j. So we're dealing here, It says here we're dealing here in the entries that are in the first row, and the A's A1 A11 A12 ... A1n. So the A's here are all the entries along the entire first row, and each entry you multiply that by its cofactor, which means the minor with a plus or minus sign. So notice, so basically this is going to be a plus. That's going to be this C is going to have a minus in it, plus minus, and so on and so forth. And that's how it works. Let's oops. Where are we here? I think I gotta pause a little. Now, when you use this definition to determine to evaluate the determinant or determine the determinant, you are expanding by cofactors in the first row, which kind of implies that there are other ways to do it. You can do the second row, third row, fourth row. It turns out that you could actually. We're gonna be mostly doing the first row. It's it's easier. Well, I shouldn't say it's easier, but it's all things equal, usually we do the first row. But actually, we're going to learn that you could expand along any row or any column and still get the same answer, which is quite miraculous. Anyway, find the determinant of A is equal. Here's our matrix A. Okay, so the determinant now, C11 is -1 because -1 times 1 minus 0 is -1. C12 is 5 because if I knock out the rows in the column, so 3 times 1 minus 4 times 2, that's -5. That's 3 minus 8, which is -5. But C12, 1 plus 2 is an odd number, so it's -5, and so on and so forth. So the determinant is going to be, we're going to take these three numbers, 0, 2, and 1. 0 times -1 plus 2 times +5 plus 1 times +4, which becomes 10 plus 4, which is 14. By the way, as I said, you don't have to go along the first row. You could do this you could use any row or any column to do this. And usually, you want to find the one, whichever column or row has the most zeros in it, that's what you want to use. Because notice that when I have a 0 here, I don't have to deal, I don't even have to figure out C11 because it's just going to get multiplied by 0 anyway. So the more zeros you have, zero. So when it comes to matrices and determinants of matrices, zeros are your friends. Okay, let's moving on. Let's see. So it's defined as an expansion by cofactors in the first row, but it can be shown that a determinant can be evaluated by expanded any row or any column, which is what I've been telling you. You could expand in the second row, and in that case, you would get 3 times -2 plus -1 times -4 plus 2 times 8, which winds up being -6 and +4 and +16, which becomes 14. Or you could have gone along the first column and you get these numbers and it also comes out to 14. And you could try other possibilities on your own, and that it works with any row. And this, I just want to say, this fact, the fact that expansion by cofactors works on any row is known as Laplace's theorem. Laplace's expansion of a determinant, and it's if you remember Laplace, if you ever took differential equations or anything like that, or calculus, there's a famous saying of a Laplace transform. Same guy, it's the same Laplace. Anyway, so he was quite active. So that's awesome. But what this is basically saying the same as our original definition, only instead of in our definition, we did the first row. Here we're saying use the ith row. So I1, I2, IN, and or the jth column, 1J, 2J, NJ. So there you go. And so it works any row, any column. And like I say, I usually look for the row or column that has the most zeros in it, because that's going to make things easier as possible. So let's find a determinant of a 4x4 matrix. Okay. and this is going to be a lot of fun. Now, of course, doing a 4x4 can be a lot of work. Not hard, but just a lot of steps. So, and again, I want to do all these by hand. I don't want to. I know you could just plug this into a calculator or whatever, and just pop out the answer. But I want you to do it by hand, because when you do it by hand, you get a feel. It's one thing, we're not. If we're doing a 27 by 27 matrix, or 142 by 142 matrix, that's one thing. But these are relatively small. Do it by hand. You get much more of a feel of what's going on, and you'll understand more of you just understanding things better when you at least for this semester do things by hand. That's the best I could say. Anyway, so I want to find the determinant. Well, I'm looking at this thing, and I notice you have all these zeros here in the third column. So I would expand it by the third column, and then I only have one thing to do. I just have the 3 right there, which is going to be plus minus plus, so it's going to be positive. Plus minus plus, so it's going to be positive 3. And then that's going to be times this times just this one term, the negative 1, 0, 3, 1, 2, 4, and 2, 3, negative 2, which is what we have right here. So all I got to do, all I got to do is figure out this one determinant. It's a 3 by 3, and a 3 by 3. Well, I'm going to have to you do that with what do you call it? A bit. I'm getting tongue-tied here. I'm gonna have to do that with cofactors to break it into 2 by 2s. See, the only 2 by 2 you could just spit out, the determinant. The other ones you got to do that anyway. So let's see. So now I see a 0 there. Oops. I see that 0 right there. So I want to make use of that. So I'm going to go along the second row. And so the first cofactor, I don't even care, because it doesn't matter, because it's just going to get multiplied by 0. So we just have to worry about the 2 and the 3. And so it's 2 times negative 1 to the 2 plus 2 power times the determinant of this minor, plus 3 times negative 1 to the 2 plus 3 power, which is going to be negative, times that determinant. And that becomes 0 plus 2 times 1 times negative 4, plus 3 times negative 1 times negative 7. And why is that negative 4? Because it's negative 2 minus 8. And that, sorry, wrong one. That's positive 2 minus 6, which comes out to negative 4. And this is negative 4 minus 3, which comes out to negative 7. And then, so that's negative 8 plus positive 21, which comes out to 13. So the determinant of that big 4x4 matrix is, don't forget, 3 times 13. Don't forget the 3. It was the 3 that the 3 was the this 3 right there, because we had to multiply by that 3, and it's positive 3, not negative 3. All right, we're doing good now. So let's move on. And boing. Okay, so here's something that if any of you ever took Calc 3, multivariable calculus, you may have learned about something called a Jacobian. And a Jacobian is basically a determinant of partial derivatives. So again, it's just some cross-pollination between linear algebra and calculus. If any of you took differential equations, there's a lot of cross play between linear algebra and differential equations, at least linear differential equations. Okay, moving on. Triangular matrices. A triangular matrix, that's one that's, see, we talked about LU factorization. And so this is an upper triangular, and that's a lower triangle. So that's the U, that's the L. Well, the determinant, if I'm going to take a determinant, I would just go along this first row right here, and make it easy. And then all I have to do is worry about this guy right there. But then I for this guy, I will go across that. I meant row. I meant column. It doesn't matter. And then so on and so forth. What winds out is that all you're going to be doing is everything is going to disappear. You're just going to be multiplying all of the elements on the entries on the first main diagonal. So if A is a triangular matrix, then the determinant is just the product of the entries along the main diagonal. And that's really kind of for the reason I showed you. Everything, because everything else besides that just kind of zeroes out. So here's a fancy proof. I'm not even going to go through it because it's pretty common sense. Okay, excuse me. Let's do an example. The determinant of this matrix A, well, it's just going to be, just go down, because of all these zeros here, this is lower triangular, so you just go straight down the diagonal. 2 times -2 times 1 times 3, which is -12. And that, my friend, is the determinant of a triangular matrix. It's very simple. And again, it's because of all that plethora of zeros and zeros. When it comes to determinants, zeros are your friends. Remember that, zeros are your friends. Well, this concludes 3.1, and we will see you next time. Bye.